All right. Well, good morning. Today what we're going to do is we are going to kick off the next unit of the year. And guys, this unit it's short and it's very practical. There's frankly not a lot of conceptual stuff in this. You're going to find, this is weird, that the test that we take over this unit is 1 page long and it is all handwritten. So guys, you know in this class that we talk about the idea of the difference between the things that you need to know and the things that you've got to be able to do. Well, this unit, guys, is all about do's. So in this unit, you are going to learn to write the formulas for what we call simple salts. Then you're going to learn to write the formulas for what we call complex salts. Then you're going to learn to write the names for both simple and complex salts. And then you're going to learn to write the names and formulas for molecules. So guys, literally any conceptual stuff that you learn in this unit is all meant to allow you to be able to write the names and formulas for simple and complex salts and molecules. So guys, all of this stuff are skills and things you need to be able to do. But in order to do that, there are some actual conceptual things that this is all based on. So in order to engage in what we're doing today, you're going to need your periodic table. And you are going to need, obviously, a sheet of paper and something to take notes with, a pencil. So assuming that you're all settled, we're going to go ahead and get started. And I would encourage you not to write any of this down. But guys, we do need to remember that when we talk about salts, if we think about our periodic tables, when we talk about salts, we are talking about a metal bonding to a non-metal. Guys, remember that the metals, they are they're small and strong. Sorry, the non-metals are small and strong. The metals are big and weak. The non-metal steals from the metal, and that creates an ionic bond. So, reminding ourselves of those ideas and hoping that hoping my board will let us switch. It goes like this. Please remember these things about metals. Again, you probably don't need to write it down. Metals are big, metals are weak, metals give away electrons, and they form positive cations. Similarly, guys, non-metals are small, they are strong, and they are electron acceptors, and they form negative anions. Now, guys, these then combine, negative ion, positive ion, to form compounds with ionic bonds. We call those salts. Of course, today what we're going to do, given the title for your notes, is we're going to develop a system for writing the formulas for these salts, the chemical formulas. Now, guys, in order to write these formulas, and this you do need to include in your notes, in order to write these chemical formulas, again, in your notes, we need to understand what chemical formulas are. So chemical formulas communicate two types of information. So fundamentally, they represent chemical compounds. H2O is water. NaCl is salt. C6H12O6 is sugar. Things like that. So when we write a chemical formula, what we're doing is we're representing a chemical compound. Now, this provides two types of information. One is composition. Water is H2O. It means it's composed of hydrogen and oxygen. Salt is NaCl. It's composed of sodium and chlorine. So one of the things that chemical formulas tell us is composition. The other thing it tells us is the ratio of the things that make up this compound. So let me show you some examples. You don't need to write these down, but let's talk. This is actually the chemical formula for sapphire. This is 2 aluminums bonded to 3 oxygens, and this is sapphire. So what do we know about sapphire? As we just said, this is aluminum bonded to oxygen, but we know that it's 2 aluminums bonded to 3 oxygens. And now we know some things about sapphire. Now similarly, we have something like this. This is what is called calcium fluoride. But now we know some things about this salt. By the way, we find this in toothpaste. It makes our teeth stronger. So we know what this is made of. It's made of course, calcium and fluorine. But there are two fluorines. Now, is it okay to say that there is one calcium because there's an understood one there? And so, guys, this is another chemical formula. Now, looking ahead a little bit, next time we're going to start talking about chemical formulas for things that are a little more complicated. This is not a simple salt, this is a complex salt, and this is what is called barium nitrate. Now, barium nitrate is composed of three different elements: barium, nitrogen, and oxygen. But now the question is how many? And the answer is it contains one barium. But now what about the nitrogens? Well, if you look at the nitrogen, it contains one nitrogen. But you'll notice that there's a 2 over here saying that we've got 2 of this whole thing, which is NO3. So we have 2 1 nitrogens for a total of 2 nitrogens. And if this makes sense, we've got 3 oxygens, but 2 of those, so that means we've got 6 oxygens. So in the end, this is 1 barium, 2 nitrogens, and 6 oxygens. Again, these are chemical formulas. What you're going to learn to do today is write these chemical formulas for simple salts. Now, in order to do that, we need to come back to a familiar friend. We've talked in the past about something called the octet rule. And guys, I really think you don't need to write this down. The octet rule is simply the rule that says atoms want a full shell of 8. This leads us to an idea, and this you need to write down. These are what are called oxidation numbers or oxidation states. We're going to use those terms interchangeably. When you get into college, even in AP, we'll talk about the fact that they are a little bit different. But guys, for our purposes, oxidation numbers and oxidation states are going to be interchangeable. So what are oxidation numbers or states? And the answer is this. These are the charges that atoms take on when they bond ionically. Give you a moment to write that down. And then we're going to talk about some examples, and you're going to find out that this is familiar. So guys, let's look at an example together. Find chlorine on your periodic tables. And guys, actually better yet, find fluorine on your periodic table. And when you find fluorine on your periodic table, you find that it is element number 9. And it is in the 7th, or the halogen group. And so we know that fluorine has 7 valence electrons. So how many electrons does it want to get 8? And obviously the answer is it wants 1 electron. So when it picks up that 1 electron, its charge becomes -1. Now let's look at another example. Let's take a look at, let's say magnesium. Magnesium is a metal. It is on the left-hand side of the periodic table. And guys, if you look at magnesium, element number 12, it's in the 2nd group. And if we remember, that means that magnesium has got 2 valence electrons. But remember that magnesium is a metal, and metals are big and weak. So guys, what that means is that magnesium cannot pick up 6 valence electrons. It can't do that. It can't pick up any valence electrons. So what does magnesium want to do? Well, it has to give away electrons. How many electrons is it going to give away? Well, it's going to give away 2. And when this gives away 2 electrons, its charge becomes +2. Now guys, going back up and looking at fluorine, remember when fluorine gains an electron, its charge becomes -1. So these numbers, -1 and +2, are the oxidation numbers or oxidation states for these elements. But now guys, do this with me. Look at magnesium and look at fluorine on your periodic tables. And if you look above the Mg, magnesium, and the F for fluorine, you'll notice that these numbers are on your periodic tables. Up above fluorine, there's a very, very small -1. And then, guys, up above magnesium, there is a very small +2. Guys, these numbers are the oxidation states, the oxidation numbers. If you look down at the key in the bottom left-hand corner of your periodic table, you'll notice that there's a thing that says oxidation states. And there's a line, an arrow drawn to where those are located. But now, guys, allow your eye to do this. Start with element number 3, lithium. It's got 1 electron. It gives it away. That makes sense. It's +1. Go to number 4, beryllium. 2 valence electrons. Has to give them away. +2. Then, guys, look at boron, element number 5. 3 valence electrons. Has to give them away. +3. But now, guys, continue on. Oh my. Carbon. Gives away 2, gives away 4, takes in 4. +2, +4, -4. But guys, if you want to get really crazy, look at nitrogen. Guys, nitrogen has so many different oxidation numbers. Remember, the negative numbers means takes electrons in, the positive means gives them away. But guys, nitrogen is like totally wackadoo. But then go to the next one. Oh, oxygen. Oxygen's got 6. It wants to take in 2. -2. That makes sense. Look at fluorine. Got 7. Wants to take in 1. -1. That's okay. Neon. 0. Can't do anything. So guys, the question becomes, how do we deal with this? Because the reality is, back to the notes, back to the wall, guys, many of these elements have really complex sets of oxidation numbers. Some don't. Boron doesn't, lithium doesn't, but carbon and nitrogen do. Oxygen doesn't. Carbon and nitrogen have got lots of messy numbers. So the question is, how do we handle that? If we've got a bunch of different oxidation numbers, which ones do we use? Well, guys, these are the rules. If you're talking about the metals, if there's only 1 oxidation number, obviously, you're going to use it, right? Lithium is +1, beryllium is +2, magnesium is +2, so on. Aluminum's +3. If it's only got 1 oxidation number, you're going to use it. Now, what if there's more than 1 oxidation number? And the answer is, you have to be told which number to use. And the way that you are going to be told which number to use is with a Roman numeral. Now guys, if you don't know your Roman numerals, here you go. Write them down. I is 1, double I is 2, triple I is 3. Then IV is 4, V is 5, and IV 4 means subtract 1 from 5, that's 4. Then guys, V is 5, VI is 6. Now V is 5, I is after the V, so you add, so that's 6. Then V double I, that's 5 plus 2, 7. But then guys, you'll notice we didn't do 8. Why didn't we do 8? Because the elements with 8 valence electrons are noble gases, and they're good all on their own. So guys, the bottom line is this. Take, for example, me grab a pen. Take, for example, carbon. And say that we wanted to do carbon. And if we look at carbon, carbon can be +2, +4, or -4. So how do we communicate which one to use? Well, if we want to do +2, we call it carbon +2. Or carbon, not +2, carbon 2. If we want to use +4, then it's a Roman numeral 4. So the Roman numerals tell us which charge to use. But again, that's only if there's more than one charge. If we have aluminum, that can only be +3, so we don't use the Roman numeral. Okay, so now what about the nonmetals? Well, guys, the rules with the nonmetals go like this. It's not letting me switch. Let me try again. No. Hang on. This is going to freak out for a second. Okay, coming back. So what about the nonmetals? Well, the rules are this. Guys, if it's a nonmetal, it wants to take in electrons. Therefore, you're going to use the negative charge. Let me show you an example. Go ahead and write this down first. All right, if you look at chlorine, element number 17, +1, +3, +5, +7, -1. But guys, chlorine is a nonmetal. It's small, it's strong, it wants to take in electrons. So guys, what that means is for our purposes, all we're going to use for chlorine is -1. So you're going, wait a minute, what about the positive ones? And guys, the answer is chlorine can also engage in some bonding that's way beyond what we talk about in this class. So we're not going to worry about it. So for our purposes, chlorine would be -1. Now, what if there's more than one negative charge? Well, guys, then what we're going to do is we're going to use the charge that is indicated by the group. So, for example, look at nitrogen. Give you a second to write this down. If there's more than one charge, we're going to use the charge predicted by the group. So, guys, look at nitrogen. Nitrogen is in group 5. So, if we look at nitrogen's Lewis dot structure, it has 1, 2, 3, 4, 5. It has 5 valence electrons. That would lead us to believe that it wants 3. But if you look on your periodic table, nitrogen, element number 7, can be +2, +3, +4, +5, but then -2, -3. So which one are we going to use? Are we going to use the -2 or the -3? And guys, the answer is we are going to use the -3 because nitrogen has room for 3 electrons. So if you want, you could even, in the box for nitrogen, just circle -3, and then you'll know that that's the one to use. Okay, so now guys that we've got that all in place, we are now going to start talking about how to write chemical formulas. Now guys, please don't write anything down that is about to come up on the screen. These are general principles. So again guys, you don't need to write these down, just follow along. So when we are writing chemical formulas, there are 4 general rules that we need to follow. Just don't write them down, just trust me. Rule number, and what we're going to do is we're going to let table salt, which is NaCl or sodium chloride, lead us to these rules because guys, these rules we actually already know. So rule number 1 is this. When we write chemical formulas, they're always written metal first. So guys, think about table salt. You have never seen table salt written ClNa. It just looks dumb. Why is it always NaCl and not ClNa? Because sodium's a metal and chlorine's the non-metal. Always metal first. The beauty of it is the metals are on the left on the periodic table, so if you read them off the periodic table, they're always in order. Rule number 2 is this: salts always have a neutral charge. Now guys, how do we know that that's true? Because you ain't never seen table salt NaCl2. The idea is this: if you look up the charges for sodium and chloride, sodium is +1, chlorine is -1. You don't need 2 of them to balance the charges. So guys, that's why salt is 1 Na and 1 Cl. We're just balancing the charges. So then guys, number 3. When you name these salts, you don't change the name of the metal. You have never heard of sodiumide chloride. You don't change the name of the metal. But guys, when we name these, we do change the name of the nonmetal. We drop the ending and add IDE. Because we know this because you've never heard of sodium chlorine. What you have heard of is sodium chloride. Again, the idea is that we drop the ending and add IDE. Okay, so guys, with this in mind, there's one more thing that we need to go over, and then we are ready to start writing chemical formulas. Guys, the last thing we need to do is we need to talk about the concept of least common multiple. Guys, don't write this down. This is math from a long time ago. We just got to make sure we can do this. Least common multiple. So for example, let me give you these two numbers, 4 and 6. What is the least common multiple? Now guys, many of you right now are either thinking or saying the number 2. Guys, the number 2 is the lowest common factor. That is not the least common multiple. So how do you find the least common multiple? Well, you need to know the multiples of 4. 4, 8, 12, 16. You need to know the multiples of 6. 6, 12, 18, 24, and so on. So where do these first meet up? They first meet up at 12. Now guys, the question is this: why on earth do we care about that? Well guys, imagine this. Imagine if we had a metal and that metal had a charge of +4. And then imagine that we have a non-metal and that non-metal had a charge of -6. Now remember that when we write these formulas, the positive charge and the negative charge have got to balance. So where is the first place that +4 and -6 meet up? And guys, the answer is right here. The first place that these meet up is 12. So in order to do this, we need 1, 2, 3 of our metal atoms. Then to make a -6, we need 1, 2 of our non-metal atoms, and that would make the formula for our salt Me3Mn2. So again, guys, this least common multiple tells us where the positives and negatives balance. If we have a +4 charge, we need 1, 2, 3 to get to +12. If we have a -6 charge, we need 1, 2 to get to -12, and that leads us to the number of atoms in the chemical formula. Okay, so guys, bringing that back to the point, why is it that we care about least common multiples? And the answer is because we use these to figure out where the charge, where the positives and negatives will balance, and that determines the ratio. If you want to write that down, I'll give you a second. If not, that's fine too. And guys, again, that's really not critical to get into your notes. so long as you remember what least common multiples are. Okay, so now let's get to it. We are now ready to start writing chemical formulas. There are steps to this. If you find them helpful, write them down. Guys, step number 1 is this. Write down the abbreviations of the elements. And guys, please understand, capitalization matters. Then guys, step number 2, find out the charges. This may require that you look at Roman numerals. Then step number 3, you need the least common multiple. Then guys, after that, step number 4, how many of each ion do you need? And then I know I'm going a little fast, step 5, last step, write the formula using subscripts. Now guys, we're going to do 3 of these together, and then you're going to have time to practice on these. Now guys, please understand, there are some tricks, there are some weird things that happen. So we're going to work on these together, and I'm going to share with you some of those things. So again, the steps. 1, abbreviations. 2, charges. 3, least common multiple. Then guys, step 4, how many of each ion do you need? And finally 5, write the formula using subscripts. So with that said, here we go. Do them with me. Guys, we're going to write the chemical formulas for these compounds. The first one that we're going to do is calcium nitride. So join me and let's do this. So guys, calcium is element number 20. It is Ca. Notice it's big C, little a. Now guys, we got a problem. Nitride is not an element. There's no nitride on the periodic table, but we remember we changed the ending. So nitride is nitrogen. Step 1. Now step 2, we need charges. You find calcium on the periodic table, it's element number 20, its charge is +2. Then guys, you look at nitrogen on the periodic table, holy buckets. So many different charges. But guys, what charge did we already agree we were going to use? -3. Okay, now guys, the next step, step 3, least common multiple. If you can do this in your head, great, but I'm going to take the time to do it. The multiples of 2 are 2, 4, 6, 8, and so on. The multiples of -3 are -6, -9, -12, and so on. So the question is, where do the positives and the negatives first meet up? And guys, the answer is 6. The positives and negatives will meet up at 6. So, how many positive 2's do we need to make +6? Well, we need 1, 2, 3. So that means we're going to have Ca3. But then, how many -3's do we need? How many -3's do we need to get to -6? Well, we need 2. 1, 2. So this would be Ca3N2. Now guys, what I'd like to do to reinforce what we just did, again, Ca3N2, is I'd like to show this to you graphically. You know how much Miss Call loves a good animation. So guys, this is how this works. On the left, we have a bunch of calcium ions. On the right, we have a bunch of nitride ions, and we are going to bring them together inside the box to make calcium nitride. So let's bring in a calcium. What is now the charge inside the box? Well, it's +2. So now, guys, let's move in a nitride, -3. So, guys, we've got a +2 charge and a -3 charge, and those don't cancel out. So let's bring in another calcium. Now we have a charge of +4, but that doesn't balance -3. So now let's bring in another nitrogen. Now we have a charge of -6, but that doesn't balance +4. So now we bring in another calcium, and now we've got +6. So we've got 3 calciums and 2 nitrogens, and we bring that together. Oh, these wiggle because they're happy. And guys, we bring this together, and our formula is Ca3N2, just like we figured out before. Okay, so guys, let's do a couple more. The next one that we're going to do is potassium sulfide. So guys, first thing we need is abbreviations. Grabbing your periodic tables, you will find that potassium is element number 19, and its abbreviation is K. If you're really feeling brave, grab the charge while you're there. It's +1. Now guys, we need sulfide. Not on the table, but sulfur is. And guys, sulfur, element number 16 is S. While we're there, let's grab the charge. But guys, this can be +2, +4, +6, or -2. So which charge do we use? Well, the negative charge, which would be -2. Okay, so now we need to know the multiples. The multiples of 1 are 1 and 2 and 3 and 4. And then the multiples of -2 are -2, -4, -6, -8, and so on. So now, where do the positives and the negatives meet up? Well, the first place that they meet is at 2. So now, how many potassiums do we need? Well, we need 1, 2 potassiums to get to +2. But then the question is, how many sulfurs do we need? And a lot of times I hear the answer 0. Guys, the answer is not 0. 1 sulfur has a charge of -2. So we need 1 sulfur to make this -2. Understand there's an understood 1 there that we don't write. But this would be potassium sulfide, K2S. Okay, we're going to do one more together. And guys, the last one that we're going to do is this. Again, guys, do this with me. You need to have the experience of thinking through these. So guys, the next one that we're going to do is iron phosphide. So if you find iron on the periodic table, you will notice that it is element number 26, and its abbreviation is Fe. Then guys, phosphide, you may have figured out, is phosphorus. Phosphorus is element number 15, and its abbreviation is P. Now guys, we need charges. You have to do this with me. Guys, look at iron, element number 26. What's its charge? Well, it's +2 or +3. Which one do we use? We don't know. Guys, we have no idea which charge to use. Could be +2, could be +3. We have no idea. We're stuck. We can't do this. So guys, what's the problem? And the problem, joining me at the screen, lies right here. You can't write the formula for iron phosphide because you don't know which charge to use for iron. So how do we fix the problem? And guys, the answer is this. Did you see them spread out? Guys, into this space, we need a Roman numeral. And that Roman numeral tells us which charge to use. Now guys, why did I choose 2 instead of 3? Because I wanted to? We could have just as easily done 3, but it would create a different compound. And guys, understand both of these exist. I have them both in bottles over in lab. But we have chosen to use Roman numeral 2. So what does that mean? Well guys, this Roman numeral 2 tells us to use +2. The Roman numeral makes your life easier because you don't even need to look up the charge. Just use the Roman numeral. Then guys, phosphide. Looking at element number 15, phosphorus can be +3, +4, +5, or minus 3? Which one do we use? Well, it has to be the minus 3 because this is a non-metal. Now, guys, let's see if we can take a little bit of a shortcut. Instead of writing out the multiples for 2 and minus 3, can you in your mind picture that these are going to meet up at 6? The first place that 2 and 3 meet up at 6 is 6. So you do this. How many 2's does it take to make 6? And the answer is 3. Then, how many 3's does it take to make 6? And the answer is 2. And this is the formula for iron 2 phosphate. But guys, check this out. Some of you are going, no, it's not, because this is iron 2 phosphate, and there are 3 phosphates. Guys, that's not correct reasoning. The Roman numeral 2 over here does not tell you how many. It tells you the charge. And then you use that charge to figure out that it takes 3 of these. So guys, again, the Roman numeral is not the number of them. It is the charge. Okay, so guys, there you have it. We are now ready to do homework assignment number 1. Guys, you will notice in homework assignment number 1, there are 15 examples of chemical formulas that you are going to be writing. And then, guys, in addition to that, there are 3 concept questions that you're going to address. And, guys, that'll do us. Again, we've got time now to work on this well. Guys, we're going to keep phones and technology out of our spaces until we're done. And guys, if you need help on this, remember I will be back next week. But if you need help, Miss Call's available too. So guys, let's grab those homework packets. And you can probably do these on the paper itself. And guys, we're going to wrap these up. You'll probably get done fairly quickly. Just find something else productive to do for the remainder of the morning.